All right, you're good to go, Larry.
Well, welcome everyone. Again, my name is Larry Brown. I'm the Sidney Kaufman Professor of Geophysics at Cornell, and I'd like to turn this over to my colleague, John Hole, to begin the discussion.
Hey, I'm John Hole, Virginia Tech. And next slide, Larry. I think both of us have to acknowledge our many students who have been working on these data sets or working out in the field with us, as well as Walter Mooney at the USGS, who was involved in encouraging and making this happen, the data acquisition happen. And the funding here came from NSF and IRIS, and I believe that shows up on our last slide. So next slide, please. Quick outline of our talk. We're going to talk first of all why we might use a dense array. Then I'm going to give a brief outline of the mineral earthquake in Virginia in 2011. Then I'll talk about the AIDA deployment, what exactly we did in the field, and finally use some of those data to image the aftershocks. And then I'll tag team over to Larry, who will use those same aftershocks to start imaging Earth structure. And finally, Larry will finish up with a few comments on the future of dense wave field recording, in particular with the idea of listening to earthquakes. Next. So the first question, of course, is AIDA has in its name the words dense array, so why would we want to use a dense array? And I think most of us as seismologists know the answer to this, but I'm going to give you a brief outline of why we wanted to use a dense array. Next. And the short answer, of course, is aliasing. Now, aliasing is defined as undersampling of a one-dimensional wave field. Now, wave field can be in time or space, so we have to think about aliasing in time, space, and 3 dimensions, and so on. And the classic picture of aliasing shown on your screen here is a wiggle that is undersampled as shown by the dots, such that if you actually interpolate between those dots, you end up with a very different signal than what you started with. And that concept is aliasing. And the principle behind, or the rule of aliasing is if you want to preserve your signal, you must sample at least twice the shortest wavelength, either wavelength in distance or wavelength in time, that you wish to record. And in Virginia, one of our goals was to record the body waves of the earthquakes, and therefore our slowest S waves that we were hoping for were somewhere around 3 kilometers per second, and our highest frequency that we were recording was about 40 hertz. In principle, we should have had a non-aliased sampling at about 37 meter spacing. What we were able to do in reality was some more like 200 to 400 meters in line along some roads and several kilometers between the roads. And this would amount to being aliased at about 7.5 hertz for the S waves, or about 15 hertz for the P waves. And while this is still aliased at the frequencies that we were really interested in, this is at least an order of magnitude better than traditional aftershock arrays, which typically have spacings of somewhere between 5 and 20 kilometers. So we're going an order of magnitude denser spacing, and we're pushing towards grids of stations that are an order of magnitude denser than that. Next slide, please. Now, one of the other advantages when we start doing this in 2D of getting both our temporal sampling correct and our spatial sampling correct, and these are, is that we can start looking at correlations from station to station. And these are recordings of an earthquake off of the east coast of Russia, recorded on arrays in Idaho. And on the left, we have 29 stations 15 kilometers apart. On the right, we have over 2,000 stations, 2,500 stations at 100 to 200 meters, and you can clearly see a very, very different character in the signal. Now, on the left, you can clearly see the first arrival because of signal to noise, and probably a secondary arrival 10 or so seconds after that because of the high amplitudes there. But behind that, you really don't see a lot, and that's because the signal to noise in the Coda and the coherency from station to station simply isn't good enough to see what you can see on the right-hand screen. So simply by coherence, we can detect weak signals is one of the lessons on the right-hand side of this picture. And I'm looking at the bottom half of it where we can see at 40 and 50 and 60 seconds some pretty decent arrivals correlating very nicely across the array. Now, we've lost the amplitude information on the picture to the right simply because I'm plotting over 2,500 stations on way fewer pixels than that. But the amplitude information is in those seismograms as well. Next slide, please. And then, of course, there's another type of aliasing, or maybe more properly called undersampling, and that is, what is your geologic target, and are you properly sampling this? And here's a very, very simplified picture of the geology of Virginia, the very, very major provinces that make up the coastal plain through to the Appalachian Mountains. And as you can see, the US Array stations, which is a nominal 70-kilometer spacing, is actually aliasing the largest scale geologic provinces of the Appalachians. So again, another rule, the US Array TA is undersampling geology, and this is why, of course, US Array has the flex array built into it, such that you and I could borrow instruments and densify this spacing. But as a general rule, we have to think about not just our wavelengths and our frequencies that we're interested in, but we also have to look at the geologic targets and the variability that one might expect in our geologic targets, and what sampling is required to make sure that we don't miss out on that. Next slide, please. So here's another way of looking at why we might want to record the full seismic wave field, and that is to look at the earthquake Coda. And I've just arbitrarily grabbed, sorry Bruce, the Pascal logo here to point at Coda. What is the definition of Coda? And Coda is that tapering seismic energy after a recognized arrival. It is caused by wave scattering of that arrival, but it is defined as well as being incoherent from one station to the next, and therefore an unknown wave scattering. But what if our stations are close enough? What if they are not spatially aliased, such that this scattered energy itself is coherent? We may be able to identify signals inside that Coda. We may be able to use that Coda directly to image the scatterers, or to image the velocity model between the scatterers. So our Coda suddenly starts to become signal. Next slide. So here's a large list of things that I've been talking about over the last couple of years. Some of you have heard me talk about recording the full seismic wave field as a potential goal for IRIS. We're doing this at some bandwidths, but not at others. And there are many advantages to recording this full seismic wave field. And what we mean by this is by having densely sampled seismic wave fields, stations close enough together, as well as large aperture arrays, a large enough spatial extent of the array. And this allows us to do two things. First of all, it allows us to improve our traditional methods, my top arrow there. We can see smaller events simply by coherence. We can see things that are below signal to noise simply because of coherence from trace to trace. So smaller sources or phases with lower signal to noise. And of course, we all know the more stations, the denser the ray paths, the better we can do our inversions, our traditional methods for source properties and for velocity inversion. But what recording the full seismic wave field also does is it enables a whole suite of new methods, wave field imaging methods, that we simply cannot do with traditional earthquake aftershock networks or any other network where our stations are horribly aliased. We need really, really good sampling to enable these methods. And that goes all the way from beam steering, where we not only get the arrival time and amplitudes of the energy, but we actually know the directions the energy is coming from, gradiometry methods, which are somewhat similar, up to source back projection. We can directly back project our wave fields to figure out where they came from as a function of space and time. Or we can do reflection imaging as if our earthquakes were sources into the subsurface. We can do interferometry, not the version of interferometry where we simulate a virtual source, which is the common method we're using, but actually back propagating our wave fields to find out where the scatterers are, or where the reflectors or the converters are. We can also look at that as a migration problem, looking at the Coda to migrate the Coda for structural imaging of converters and reflectors. And of course, we can advance that all the way to full waveform inversion. And of course, if we're doing this with full arrays, we can do this in 3 dimensions, or when we're in situations where stress and strain are changing, aftershocks are happening, things are moving, we can actually do 4D in volcanoes or faults or situations like that. So the whole goal here of recording denser station spacing is to provide higher resolution images of both the seismic source and the earth structure around it. Next. So let's start talking about the Virginia earthquake. Next. The Virginia earthquake, as you can see in the upper left-hand corner, it occurred in 2011 on August 23rd, a little bit before 2 p.m. local time. It was a magnitude 5.8 earthquake, and it occurred in central Virginia. And that map at upper left shows seismicity in the previous couple of decades. Based on that seismicity, this is actually a previously identified hazard zone on the National Seismic Hazards Maps. It's a known zone of seismicity. Now, the magnitude 5.8 earthquake we had in 2011 is the largest event we've had in that zone, but previous events have been up to the low 5s in the late 1800s. So this is a place that has a known hazard. This is completely out of the blue. Analysis of the data from this main shock show that it occurred at 8 kilometers depth, which is pretty shallow. It occurs within what is known to be an overthrust sheet within the Piedmont province of Virginia. The Piedmont province is a series of terrains that have accreted to North America during the Appalachian orogenies. So this was part of island arcs, terrains, and other terrains floating around in the ocean that were accreted as Africa ultimately slammed into North America. And these things have been metamorphosed and eventually eroded towards relatively low topography today. The focal mechanism that we see in the bottom left-hand corner, plus the aftershocks, tell us that the earthquake occurred on an east-southeast dipping reverse fault, fairly steeply dipping reverse fault. And Martin Chapman's work with the aftershock, with the main shock, has shown that the main shock actually consisted of 3 sub-events, each of which was about a second apart. So over the course of about 2.5 seconds, we had 3 separate events. Bottom right shows this traditional USGS felt map, and the USGS claims that this earthquake, which was felt all the way from Atlanta to Canada, because it is occurring in a highly densely populated area, but also because it's occurring in the hard rock terrains of eastern US, it was felt by more people than any previous event in the United States. Next slide, please. So this earthquake did cause damage. It caused damage locally in Louisa County. You can see the bottom pictures. Things like chimneys falling down, garages, building foundation damage. Actually, some of the worst damage occurred to buildings owned by the county, such as the schools and the municipal courthouse. It also caused damage about 100 kilometers away in the Washington, D.C. area. And at top, you can see some damage caused to the National Cathedral. And on bottom left, you can see people rappelling down the top of the Washington Monument, looking at damage done to the monument. In this case, these large blocks in the monument shifted several inches, and there were gaps of several inches between the blocks after the earthquake had finished shaking. And it was closed for 3 years to repair. And this is kind of iconic in Washington. Probably the most scary part, the thing that was shaken by the earthquake, however, was up the upper right-hand corner, is that there's a nuclear power plant only 22 kilometers from the epicenter. And although there were no modern seismographs anywhere nearby, the plant was still operating a 1960s vintage scratch plate seismograph that showed that the power plant actually shook twice as hard as it was designed to withstand. The good news is it didn't fail. The power plant shut down not because of the shaking, but because of a pulse and pressure in the cooling systems, in the water in the cooling systems. It shut itself down, and inspections showed that there was no serious design, so thank God for engineers doubling the spec and doing their work very well. And it reopened again 2 months afterwards. But this is upwind from Washington, D.C., and many of the other things in the north, and population centers in the northeastern United States. So pretty scary episode. Next page. So because of this earthquake, so some of the questions, in addition to the big question, of course, of to why do we have earthquakes in the middle of a plate, were what exact features was this earthquake occurring? Was it taking advantage of an older geologic structure or a new fault? What geology was this occurring in? Was the geometry of the rupture zone? And what is the geometry of the surrounding geology? Next slide. So to answer some of these questions, many people went out and recorded these aftershocks. I'm going to focus first on traditional aftershock deployments, which is shown in the yellow stations. 4 different groups. That's the USGS, Virginia Tech, Lamont Doherty, and IRIS. Each put out 7 to 8 to 10 stations, to a total of 36 stations that were deployed, about half of which were telemetered real time. And all of these data are available through IRIS now today if you want to look at them. The station spacing was somewhere between about 3 kilometers and about 10 kilometers in this array. And next slide. These data have been analyzed by several people. I'll show a few results from the people here at Virginia Tech. And what they did was they looked pretty closely at the first 4 months of the aftershock sequence, in which time they recorded about 4,000 locatable aftershocks. The map at left shows those aftershocks as a scale bar of 10 kilometers. It's a fairly small aftershock zone for magnitude 5.8 earthquake. And what you can see at the bottom left is a cross-section, a cross strike and a long strike. Aftershock zone simulating the focal mechanism of the main shock, striked north-northeast with a fairly steep dip, 51 degrees. And probably a more interesting feature here is that almost all of the aftershocks, the black dots in those figures, are the 3 sub-events of the main shock, and almost all of the aftershocks are shallower than and to the northeast of the main shock. One of the other interesting things that came out of the focal mechanisms at the bottom right, and this is a paper that just came out in this month's issue of BSSA by Wu, Chapman, and others, is that if you look at the focal mechanisms, there's actually a depth dependence upon them, and that although all of them are reverse earthquakes, the sigma 1 direction rotates more than 45 degrees as you go from very shallow to greater than 6 kilometers depth, which is really kind of interesting. So the actual maximum horizontal stress direction seems to be depth dependent in this area. Next page. So let's come on to what we did, what AIDA did. So Larry Brown and I and our students, or let's be honest, our students, very quickly after the event put out a large number of stations. And these are the stations shown in blue on this map. This is the same map I showed you before. The yellow stations are the traditional stations. And what we did in blue is we first of all set out an array of 30 3-component instruments that are going off to the northeast, off pointing towards Washington. And that array, 60 kilometers long, was designed to look at attenuation as a function of distance, which is actually fairly poorly known in the east at distances that are less than 100 kilometers. This is because we typically have very few stations at distances of less than 100 kilometers. We're not going to talk about these data today, but that line actually goes through the nuclear power plant and points up towards Washington, so it does have some interest. In addition, we set out, it's shown in the box at bottom left, the star is the epicenter, and those lines are 148 single component stations. So the next slide, please, zooms in on that box, and as you can see in the bottom left, there's a 5-kilometer scale bar. So the white circles are the aftershocks that we're recording. The pink triangles, they change from yellow to pink, are a subset of the traditional aftershock stations, and those little black dots are 4 lines plus the blue circles, which are the 3-component ones, of the AIDA deployment. These are stations, 148 stations, single component, at 200 to 400 meter spacing along a network of roads in the area, and you can see the spacing between the roads is several kilometers. These were laid out in 2 6-day phases, and the first instruments were deployed 4 days after the main event, and they were deployed as a tropical storm was blowing through the area, so our crews got rather wet. Next slide. And the reason we're able to lay out so many instruments is that we're not dealing with traditional instruments. We're not dealing with traditional earthquakes instruments, but we're dealing with active source or controlled source instruments. What we used were the Texan Seismographs. There's a picture of one in the upper right-hand corner. These were borrowed from the Pascal repository. These were EarthScope instruments. And these instruments are very, very small, very lightweight, and very simple to use. They use a single component 4.5 hertz geophone. You can see pictures of geophone there. They can also, if we use 3 of these things and literally duct tape them or strap them together, we can attach them to a 3-component geophone and get 3-component stations as well. And these stations are so simple to use and so lightweight that we're able to deploy them in about 5 minutes. There's a picture in the middle that shows the size of one of these things in a shallow pit at the side of the road dug by a traditional pick. And because of this, we were able to put out those 148 stations with a 6-person crew, leaving the hotel after lunch and being able to be back in our hotel well before supper time with a shower. Okay, so it just took a couple of hours for us to put out these stations. The disadvantages of these things, of course, is that they're 4.5 hertz geophones, which do have a response below 4.5 hertz, but a decreasing what's the word I'm looking for, dynamic range below 4.5 hertz, and that they're 1990s technology. So as it says in the bottom right, these things have limited power. The batteries last about 3.5 days when they're on continuous record. They have limited memory. This reduced our sampling rate. These instruments are capable of 2,000 samples per second, but we only did 100 samples per second because we knew that would fill the RAM in about 7 days. And because of this, because we were going back and visiting the stations every 3 days, we did a total of 12 days of deployment, and we only put out 148 of the 2,500 of these things that are sitting in the instrument pool. Next slide, please. So a very quick look at the field data. At the upper left, we see 1 hour of data on 59 of the stations, and you can see some nice strong events going across the array. Those events that are sloping across the array, those correspond to the road speeds. So those are trucks and cars driving along the roads. But you can see at about the 1/3 of the way down, a nice horizontal event, and that nice horizontal event is zoomed in on the picture at top right, and you can see that's a 5-second window now, and you can see clear P&S arrivals from an actual earthquake. There's a single station down there at the bottom left looking like a more traditional single station, P&S wave arrivals with a P&S delay. And if you look at the bottom right-hand corner looking at that earthquake, you can see that we're getting very strong signal all the way from the corner frequency of the geophone, 5 hertz, all the way up to our Nyquist frequency of 50 hertz. Next slide. So I want to first talk about lowering the detection threshold because of our really close station spacings. Next slide. And these, again, are just raw field data. At the left, you see, I think that's 55 stations there and about 200 seconds of data. You can see a very, very strong event. That event had a magnitude of 1.8 according to the USGS. And then just a couple of minutes later, you see a much, much, much weaker event going across our array. Very easy to detect because of correlation across the array. And at right, you can see the amplitude spectrum of that event. It's about 50 dB below the magnitude 1.8. So we're looking at an earthquake that's probably about a magnitude -2. Next slide, please. So after we got back in the field, we started to sort these, and these are plots of the stations are now plotted on the horizontal axis as distance along the lines. You can see a map of the lines at the bottom right. So at this time, we only had 2 of the lines on the ground when this magnitude 3.4 earthquake happened, and you're seeing 5 seconds of data. The trace start time is just an arbitrary second mark. It's not the actual time of the event, and these stations have a 200-meter spacing along these roads. And what you can see, in addition to very, very, very clear P&S phases, is that in between the phases and after the phases, you can see some other coherent arrivals. And the cursor right now is pointing at one of the strongest of these. And these, of course, we're interpreting as either converted phases or reflected phases that are appearing within our data that are very easy to see because our stations are so close together. We can see the correlation of these events. Next slide. Later on, we managed to get all 4 of our stations on the ground, and here we are looking at a magnitude -1.5 earthquake. That's a negative magnitude earthquake, -1.5 earthquake. And here we have information that's 200 to 400 meter station spacing. You can clearly see that there's P arrivals and S arrivals in some of the stations, but it's kind of hard to see. The signal to noise here is equal to 1 or maybe even less than 1 on most of the stations. And if we go to the next slide, what I've done is I've just really taken a subset of this that shows our stations that are closest to those stations in the traditional array. And it's no surprise when you look at these that the traditional array was unable to detect or locate this event. It didn't even detect it. And on at least 3 of these traces, the largest wiggles that you see are actually not the earthquakes. If you go back to the previous one, you can see which we're at, where the earthquake was in reality, which are the P waves and which are the S waves. We've got enough curvature on these events that we can actually locate earthquakes this small fairly easily. Next slide. Next slide. So the lesson here is with the 200 to 400 meter spacing just along a handful of lines, we've got a detection threshold here that is a magnitude of about -2. Now, admittedly, here we are working in a hard rock terrain, so magnitude -2 does get up to the surface fairly easily. But with 12 days of data, we were capable of recording about 4,000 aftershocks, which is what the traditional arrays were capable of recording in about 4 months. So we get a much, much lower detection threshold. The threshold on the traditional network work was just a little bit below magnitude 0 was the location threshold. Next slide, please. So we're going to start working with these work. And one of the first things we can do, of course, is what is traditionally done with most aftershock arrays, which is local earthquake tomography. And this is work that one of my students, Kathy Davenport, was working on. Next slide. So what Kathy did was she took about 300 of the larger events. She made sure that these were nicely distributed, and she inverted both the P. She picked P times and S times, and did a traditional local earthquake tomography for both seismic velocity and hypercenters. Based on resolution tests, and there's one of those shown on the bottom left, our spatial resolution with this data set was about 1 kilometer, and this was limited more by the spacings between the lines and by the distribution of earthquakes than it was by the station spacing in lines. So having stations between the lines could have improved this. What she found out was remarkably disappointing. Unlike an earthquake in California in the San Andreas, where there's huge velocity contrast to worry about, she actually was able to fit these P and S wave times to remarkable accuracy, 16 milliseconds on the P, 60 on the S, with a absolutely constant velocity model here. So there's the velocity shown there in the VP-VS ratio, and these are consistent with felsic crystalline rocks. This is, it turns out, geologically consistent with the observation the main shock and all of the aftershocks are not just occurring within the Piedmont, but they're all occurring within a single geologic unit within the Piedmont. And we have a nearby reflection line that says, yes, they truly are occurring within a single geologic felsic terrain, crystalline rock terrain within the Piedmont. So we're getting a very boring velocity model, but that's the way it actually is. Next slide, please. Of course, the earthquakes are now located within that boring velocity model, but the accuracy of these earthquakes, and here's views of a long strike and a cross strike, the accuracy of these hypocenters, because of the very large number of stations we have, are actually less than 100 meters, and that includes the trade-off in possible velocities functions as a function of depth. So the depth trade-off, the earthquake time trade-off, and the velocity trade-off are all built into that number. accuracies less than 100 meters without using double difference methods. Now, the first thing you see if you look at the view along strike is that the cloud of seismicity is still more than 1 kilometer wide. And given that we know what the earthquake accuracies are, we actually believe that this cloud of seismicity truly is a cloud of seismicity, that the earthquakes are not all occurring on a single plane, but are occurring on a zone that has some real width to it. And this actually matches some of the hypocenters that we see, that they're not all having the same focal mechanisms. Okay. In addition, if you look at this in some detail, we can actually see some variation along strike, some about 10 or 20 degrees of curvature as we go northwards, and another 10 or 20 degrees of curvature as we go at depth. And that doesn't show up in these pictures where we've got all the data on the same plot. Next slide, please. We can also, of course, look at our up-down motion. So looking at using cross-correlation to determine the polarity of the P wave. In the first couple of days at the left, where we only have a fairly small number of stations out, we actually got all of our motion on that magnitude 3.4 earthquakes. First motions were all upwards. And if you look at the earthquake focal mechanisms from other folks, it turns out the focal plane was just off the west side of the array. But the one in the middle shows by the time we got more stations on the ground, we're actually locating the focal mechanism as it crosses our line down to a couple of 100 meters at the surface, and that corresponds to just a few degrees on the focal mechanism, on the beach ball diagram. So we actually get very, very, very accurate focal mechanisms where the array crosses the focal plane. Now we're able to do this down to about a magnitude -1, but as it shows at the right, we can't do that with the signal to noise of less than 1. So magnitude -1, which is about a signal to noise of 1, we were able to actually get focal planes where they crossed our array. Next slide. So something much more interesting that we did, a more wave fields approach to look at these earthquakes, was to use the methods of back projection. And probably most of you are familiar with Miyake Ishii and many others since her over the last decade or so have been using this back projection method to use large regional arrays, such as the US array or the Japanese HyNet array, to image subduction zone earthquakes and to directly back project the observed wave fields to find out where and when the earthquake energy was coming from as a function of space and time. Now, I've been working with 2 of my students here to do this with our recordings of the aftershocks of the Virginia earthquake. Next slide, please. So this kind of sort of explains what the back projection method is. First of all, I'd like to make the comment that for those of you who have heard of reverse time migration, earthquake back projection is reverse time migration, but we're ignoring the amplitudes. So the difference between them is actually a relatively subtle one. And if you wanted to build a proper amplitude into your ray tracing algorithm, which we have quasi-done in our case, you can actually do a full reverse time migration. But what the algorithm essentially does is, if you have a very, very, very good 3D velocity model, and this is absolutely critical, we have one sufficiently good that it's a fraction of a wavelength in accuracy. So if you have a really good 3D velocity model, as shown at bottom left, you take each and every possible place where the earthquake might have occurred, for example, that little star at the left-hand side, you take an ith possible source point, and you compute travel times from that ith source point to each and every one of your surface stations. So those surface stations are shown on the opposite side of the cube, and data from those stations is shown just above those stations. So you compute those times, and you shift the data according to the predicted travel times from that possible earthquake point to that station. You shift those travel times up, and this diagram doesn't quite show it right because they actually shift to a much earlier time, the potential hypocenter time. But if you've got the right hypocenter, those energy will line up. And you can simply stack those traces, as shown at the bottom right, and get a much larger signal to noise. And then we just do an energy on that to actually plot energy as a function of x, y, z, and t. Now, if you do the stacking at the wrong grid point, the wrong hypocenter within your 3D velocity model, the energy will not line up, and you will not get energy at that location. Next slide, please, shows some data from us actually using this method. So that's a very, very simplified version of what that method is. It's basically a stacking method about possible places where the earthquake might have occurred and possible times that the earthquake might have occurred. So at bottom, we show a rather small earthquake. This earthquake has a magnitude of less than 1. It's approximately -0.1. I've actually seen a number of -0.3 in another person looking at this one pretty carefully. And what you can see is that the P wave energy only gets out to 6 or 8 kilometers distance on these 2 lines. This is when we only had 2 lines on the ground. So it's not the best constrained earthquake. This earthquake is actually not even underneath our array. It's just a little bit to the north of the array. Migrating or back projecting the P wave arrivals gives us the images at top. And I'd like to say that there's a map view at left, an east-west cross-section in the middle and a north-south cross-section, but in each of these cases we've zoomed within our 15-kilometer cube down to a little bit more than a kilometer. So we're looking at about 4 to 4.5 kilometers depth and just locally at where this image actually had some constructive interference. And what we see is we're actually able to locate this earthquake with a spatial resolution of about 200 meters, even though you can see the signal to noise on that arrival in the data. Next slide, please. Well, sorry, stay here for a second. One thing we do see, however, particularly on the right, is you can see some artifacts caused by the fact that this earthquake is not actually within our array. So you can see that smearing. It's a typical migration artifact is what it's called in the active source business. Next slide, please. So this next earthquake, a bigger earthquake, magnitude 2.5, is also underneath within the array because by this point we had all 4 of the lines on the ground. You can see the data are actually higher signals to noise, and you can see move out on all 4 of the arrays that tells us it's within the array. And again, when we back project this earthquake, we see better signals to noise, in other words, more of a difference between the red and the dark blue, but we also see a sharper signal without those migration smearing effects because we are now properly surrounding this earthquake. And again, a spatial resolution here of less than 200 meters. That resolution is approximately the size of our dominant wavelength at 20 hertz. So that's really what we're doing. We're doing an energy average over one cycle, and that's approximately the size of this blob here. Next slide, please. I wanted to show you one more because I wanted to show you one that's a really, really, really tiny earthquake. The data are at the bottom, and if I just showed you 1 or 2 or 5 of those seismographs, you would say that there's no earthquake in there at all, or maybe there's a few random noise bursts. But you can see, because of the close station spacing, that there is an earthquake moving out across that array. The energy in that P wave is actually less than signal to noise of 1. So the signal to noise ratio is less than 1, and yet we are still able to back project this earthquake. And there's the images at the top. They're a little more blobby. They're a little more, they're not very high signals to noise, but there's this distinct event occurring, in this case, a little bit more than 3 kilometers depth with a spatial resolution of something like 500 meters. And I'd just like to make a comment that I know of 2 different cases in the industry where industry has imaged earthquakes as small as magnitude -3, with signals to noise is so small they cannot even see it in the raw data, but because they're putting out thousands of stations, they're able to actually use these back projection methods to image the events. So we can see things that are really, really, really tiny because we have many stations. Dense arrays is the advantage. Next slide, please. So to summarize quickly my part of this talk, maybe I've gone a little bit too long. Aftershock imaging with dense arrays allows us, because of hundreds of sensors, to get a detection threshold that is below a signal to noise of 1, to get velocity resolution that is really dominated in this case by our line spacing, not our station spacing, to be about 1 kilometer, to get absolute hypocenter accuracy that is 100 meters without using double difference techniques. And I think we can get down to tens of meters if we have a grid of stations. Focal planes observed all the way down to 1-to-1 signal to noise, and back projecting events that are smaller than 1-to-1 signal to noise. The one comment I'd like to make is that using these 1990s technology, 3 days going back to visit every station is a pain in the butt, and I wouldn't like to do that again. But the Virginia aftershock sequence, we've learned some stuff about the aftershocks. We're still working on those, and we've learned some stuff about the geology. And I'm going to pass it on to Larry at this point.
Thank you, John. Okay, can everybody hear me? I would like to take all that good information that John has derived about the earthquakes and then use those earthquakes to tell us more about what's going on in the surrounding medium. And my particular interest was trying to use them in the context of probably the highest resolution seismic technique we have for imaging, and that is the seismic reflection method. And we found that there were 2 approaches we wanted to look at to use those recordings to do reflection imaging of the medium surrounding the earthquakes. The first approach, which was worked on by student Diego Quiros, was to recognize that we could use an existing technology to image these earthquakes, a technology known in the industry as reverse vertical seismic profiling. The idea here is that we're all familiar with doing a surface reflection survey in which both the sources and the receivers along the surface, and on the left-hand side of this diagram we can see the kind of rate path geometry of reflections that will be recorded with this kind of typical geometry. we take advantage of the fact that multiple source receivers can give us multiple reflections from the same subsurface point, and then we can stack this image to a high signal-to-noise ratio view of what's in the subsurface. The difference with an earthquake, of course, is that the source is not at the surface, it's at depth, and the geometry of the ray path to reflections of the subsurface varies not only in terms of time, but in terms of the spatial position of the reflection point. Now, it turns out this geometry is well known in the oil exploration industry in a technique known as vertical seismic profiling. It's usually called reverse seismic profiling when the source is actually downhole. And this geometry of having a downhole control source record the surface has led to a whole imaging technology that we can simply apply to natural sources such as earthquakes. On the left-hand side are a couple of records of one earthquake along two different lines, an inline and a cross-line records, similar to the ones you've seen earlier. In this case, the S wave has been muted so it doesn't get in the way. And in the right-hand side is to show you what we're going to try to do is take the energy from the earthquake to the subsurface and reposition that energy that corresponds to reflected energy to the right time, depth, and horizontal position where it's hitting the interface. That requires shifts not only in vertical time as you would have in the normal move-out correction for a surface source, but also has a correction in position where the energy is coming from for a particular source. So it makes it a little more complicated. This is taking that same data and doing a reverse VSP, common reflect point mapping for a similar earthquake, which shows what you see as a reflection image for any reflectors containing this data. On the right-hand side is shown in a raster mode in two different three-dimensional views that were produced by looking along these two different lines. And for example, the strong coherent event here corresponds to the strongest reflection we see in the data, and you can see its geometry as it's projected in these two different views on the two different lines. This shows a little bit better where the two lines are actually looking at their intersection. So in fact, we get a three-dimensional image of the reflections, in this case from a single earthquake. The problems we have are that we have many earthquakes, and the idea here is we'd like to take advantage of all those earthquakes for two reasons. One is each earthquake interrogates a different part of the subsurface, and secondly, those subsurface interrogations overlap to provide redundancy that we can use to do the common reflection point stacking that we're used to in the surface. In order to make this work, however, we need to have accurate hypocentral locations and origin times for these events. And of course, with these arrays, as John has mentioned, we actually have very accurate hypocentral locations. We also need to consider the fact that the source may not be the same for each event, and we have to correct for source wavelet variations, particularly those related to the focal mechanisms. The point I want to stress here, however, is that we also need to take advantage of having the proper recording array at the surface to maximize both the subsurface coverage and the reflection illumination. Our first attempts to stacking were not very satisfactory, so we decided to look into at least the effect related, to the issue of the recording geometry. And this was done by Diego by building a simple synthetic model of reflecting interfaces in the subsurface that's meant to kind of simulate some of the geometries that are inferred from a previous common reflection point surface seismic survey that was carried out in the late 1990s and published recently in a paper by Tom Pratt et al. And Diego decided to see what would be the illumination characteristics for earthquakes with the same geometry as the given earthquakes that were recorded with both our given surface array and then compare that with what we'd expect from an ideal surface array. Here is an image showing the surface array that were used in Virginia in blue, the red dots being the earthquake locations or a subset of the earthquake locations that are better located from that event, and the yellow and green dots here are the portions of the subsurface for two of the particular interfaces that were meant to reflect these thrust sheets. What we found is, of course, that the spatial density of coverage was very variable, where we have some areas with very little coverage, some areas with a little better coverage, but large gaps in the coverage which reflect themselves in a 3D image as being spotty in terms of its coverage, but more importantly, with very little redundancy to work on signal to noise. If we had been able to put out a true surface 2D array, such as shown here, and try to image the same set of reflection subsurface earthquakes here, we could expect to get a much more robust image and a more continuous image of both of the subsurface interfaces in 3D. I would show you the imaging illumination map over here, except there was so much redundancy it blew up the computer when this model was actually run. But the lesson here is that in order to do a proper job of 3D imaging, in order to do the proper job of stacking, we really need to have a 2D surface array. Okay? We'll say more than that, and then I want to move on to a second independent approach to doing reflection imagery, and this one is taking advantage of the principles of seismic interferometry. And this is work done primarily by Doyen Kim, a graduate student at Cornell. Now, many of you are probably familiar with seismic interferometry as it's applied to the study of surface waves in what's sometimes called ambient noise imaging. It turns out that the same principles will apply to body waves as well, except the geometries are a bit different. The kind of ideal situation to image with a reflection experiment would be in a 1D world. This is an example which is to illustrate a principle that was first espoused by John Clare about 1968. On the left-hand side is a simple layered seismic geometry, layers with different velocities and therefore different reflection coefficients at the interfaces. And what's shown here is a synthetic seismogram that would be recorded if there were a subsurface source at the depth here recorded directly above at the surface, again a 1D world. If you were to do a cross correlation of the record here with itself, that is with the station acting as a point on the surface as well as a recorder, you would get the autocorrelation function here of the transmission response. On the right-hand side is shown a synthetic reflection record that is generated by putting a source at the surface at the same position of the recorder and then calculating the traditional reflection response. This would be the traditional surface reflection survey result we'd get for a coincident source receiver, and you can see there is a virtual exact match between the reflection response and the autocorrelation of the transmission response. That is, the source here has been repositioned as though it were at the surface to produce a reflection image. This is sometimes called redatuming, and the move source is sometimes called the virtual source here. An important thing to notice in the one-dimensional world is the position of the source doesn't matter. The depth of the source is irrelevant, ignoring amplitude effects such as spherical divergence and attenuation. In terms of travel time, this record would be the same no matter where you put the source in depth. It becomes independent of the position of the real source. It only depends on the position of the virtual source. Now, in the real world, of course, these sources are not vertically stacked for us, and moreover, we like to use this using not just a single geophone, but an array of geophones. And this is a widely circulated version of an illustration for seismic interferometry for body waves with subsurface sources. And the illustration is meant to show that if you take the record of a subsurface source recorded at a seismograph at a position here, and you correlate that record with the energy that would come up from the surface and be bounced from the surface as a multiple back down and reflected off a target interface back to another geophone at some distance here, the correlation of this record with this record here and here gives you this record, which is effectively, at least in terms of time and spectral content, the signals you would get if the actual source was really located at this virtual source position. You have actually turned a subsurface source into a virtual source to surface, and now we can process this the same way we'd do if we're doing an exploration survey using vibrosize or explosions. Now, in interferometry, there's another important step, and that is this really only works if you have a large distribution of sources in the subsurface that have a range of depths and a lateral distribution such that when you add up a large number of these sources, only those sources which share this particular entryway to this reflection add constructively so that the sum produces effectively a signal here that stands out from the noise. As in the case of vertical, however, the position of the sources are irrelevant as long as they share some leg of their journey which is collinear with this particular source. So, for example, this source could be at any depth as long as it lie along this line, or it could be any other source as long as some scattering from that source came up in this particular direction. We tried this with the data right off the bat, expecting to see some beautiful results, and what we got was, in fact, when we did the cross-correlation of the raw recordings, which were, of course, the earthquakes and all the other noise, we got pretty much an uninterpretable mess. So we decided to try to take it apart to see how do we do this properly so we can use the earthquakes to do a credible job of imaging. So we began to look at the problem is what happens if we have a limited number of sources. They're not large numbers, but a handful or even one. And what would happen if the sources are not distributed in the sort of quasi-random large distance span and depth span that you would expect for traditional seismic spectrometry as it's used in the context of ambient noise imaging. Okay, and I'm going to show you some results of some synthetics by DK in trying to understand how this works, and then how we can apply it to individual earthquakes and then sums of sets of earthquakes. The left-hand side is a synthetic seismogram that corresponds to a surface source that is recorded by geophones along the surface. The arrival here is the direct wave traveling from the source along the surface. This is a constant velocity medium. The second energy here is the conventional reflection going from the subsurface, showing the hyperbola that we've now come to know and love. Over here is the record we would expect in these ideal conditions for a single reflector, but with a subsurface source. And we would see this wave here is a direct signal from the source to the surface. This wave here actually corresponds to energy that goes downward from the source to the reflector if it exists below it and back to the surface. And this wave here corresponds to energy comes up, is reflected back from the surface, and then interrogates the subsurface that comes back here. So this is the wave that actually corresponds to the previous diagram we looked at. So we have a lot of energy to deal with here for a simple source, but ideally we could expect to see reflections both from a downgoing wave and an upgoing then downgoing wave for this simple case here. The next diagram shows what happens to the data after we cross-correlate. On the left is our shot gather we see here. On the right is actually taking the previous real shot gather and cross-correlating each trace in that shot gather with the trace that corresponds to this virtual source. So we're going to try to turn this station into a virtual source. If I go back a second, we're going to take the data here, this trace, and cross-correlate with all the other traces in order to generate a virtual source by the principle we talked about earlier. So this is the cross-correlation result. You can see that it has also many rivals in here. The arrival at the top here is actually the cross-correlation of the direct arrival with the direct arrival recorded at all the other stations along here. The energy here corresponds to the cross-correlation of the direct arrival with the downgoing reflection that occurs at all the stations across here. And this corresponds to actually redataming the virtual source or redataming the recording to a depth level which corresponds to the actual depth of the source. So we're actually generating a reflection survey as though we had the sources at the depth of the earthquake, and we're recording the sources at the depth of the earthquake. This source here is the one we're interested in primarily, and this corresponds to redataming of the earthquake to a surface source, and the one we want to use here. But we still have, in addition to this, these other ports of energy to play with. Here we show, for reference here, again, the result of a single source here that has been cross-correlated. On the right-hand side is a series of earthquakes scattered in depth in which we have summed all of the shot gathers for each individual source to present a composite source. We can see that the energy for the direct arrival and particularly this downgoing wave is spread out in time. It's not coincident for the different sources here. They are spread out and are not coincident. They are not constructively interfering with each other. But all of the reflections that are from the wave that goes up and down are actually coming in at virtually the same time at offsets near the surface position, and they only veer off as you go to larger offsets. That is, they're constructively interfering for the downgoing wave, but not for the other waves. Okay. Now, you might recognize this pattern as something we call normal move out from a surface source. And here, DK has shown the expected normal move out curve from a surface shot here. This would be a real-world seismic survey. And on top of that is the virtual reflection that we get by cross-correlating this record with all the other records for a subsurface source. And what you can see is that for small offsets, the two are collinear. Therefore, if we apply a conventional normal move-out record, as shown on the right, we can see that we flatten both the real surface reflection here, and we could then add all these traces to stack it, which is what we do in common reflection point stacking for increase in signal noise enhancement. And we could also get the same effect for at least a range of offsets between our virtual source and our real receivers for the virtual shot. And if we limit our attention to this range here, we can therefore stack an image over a fairly large range of offsets of earthquakes which are located away from the source here. We're no longer restricted looking only earthquakes vertically below. On the right-hand side is a plot for a particular wavelength of how far that offset could be for a particular range of depths in the subsurface here. So what's been done here is to calculate a series of synthetic shot gathers from multiple sources in the subsurface, and what's seen here is the stack of all of those synthetics, pretty much a mess for a shot receiver for a virtual source here, a virtual source in the middle, and a virtual source in the end. And down below are these virtual shot gathers which have been to which a normal move-out correction has been applied. Again, these are virtual shot gathers, but they would be equivalent to common midpoint gathers for flat reflectors. And you can see that we are getting flattening out of energy for all of the reflections from all the earthquakes at the same time at near source offsets. If we take this data now and do common midpoint sorts, and then normal move-out correction and stack it, we get what we see here. On the left-hand side is a simulation of a surface reflection survey with 3 shots at the surface, applied with a conventional normal move-out correction and stack, and you can see it gets a very good image of the reflection in the subsurface. On the right is what is achieved the equivalent. In this case, though, the sources are these sources scattered in the subsurface. They have been used to produce virtual shot gathers across the line here. Those virtual shot gathers have been treated the same way that the real shot gathers at the surface have been applied, and we can see that we do recover a nice amplitude for the target reflector, and we still get some energy that's coherent for this quote-unquote artifact, but it's actually the reflection from the downgoing wave. If, in fact, there were a larger range of earthquakes and more earthquakes, this artifact would eventually stack out. So how does that work with real data? This shows a set of earthquakes from Virginia that DK has used to calculate real virtual shot gathers with real data, and then CMP processing and stacking. And you can probably convince yourself that there is coherency at depth of some of these arrivals here. Again, I think there is a bit of the eye of faith for some of us here, but we've seen worse data with control source data. On the right-hand side is actually that surface reflection survey that was published by Pratt et al. And reprocessed recently in the same area that spans the aftershock zone here. And you can see that the area where we see coherence down here does correspond to an area where there is reflectivity on the surface energy, although the data here at depth is not that as good as well. One of the big differences here, to reemphasize a point made by John, is that this is with a surface recording interval of 200 meters. This was with a control source surface interval of 67 meters. So a large factor increase in densification in the control source beyond what we achieved with our AIDA array, which is, of course, much denser than any conventional array. So what does this imply for the future of dense arrays? Well, clearly we need more dense spacing even than what we have, and we need larger coverage than what we have, which leads us to consider arrays over large distances. At the same time we were working on this experiment, results were coming out from oil industry surveys using new generations of recording technologies, the best known of them being the Long Beach experiment, in which thousands of channels were deployed for an oil exploration survey. And unlike past oil exploration surveys where these were often turned on only for a short period of time during an explosion, these were left to record continuously for substantial periods of time, so they act as many natural source recorders as well as control source recorders. And this is one of the results of wavefronts propagating through the array from a natural event that's been reported in the literature. In fact, this data set's been worked on by many people to show lots of the kinds of data you can get with this kind of density. Notice this is at 100 meter spacing, half the density we used in Virginia. And this has been made available the fact that we now have new technologies which are both, one, portable, and two, continuously recording for substantial periods of time. The ones we used in Virginia were good for about 3 days. These can record for several weeks, up to a month or two with current technologies. And as we've seen in the industry, these are deployed in arrays that are up to thousands to tens of thousands of instruments. If we want to record wave fields accurately to do all the kind of work that John wants to do and the kind of work I want to do, we necessarily have to have a dense array. We cannot avoid the laws of physics, the law of sample processing, and if we have any kind of coverage at all, that's going to record a large number. If we were to go to 50 meter spacing, which would be much more along the lines of what the sampling theory would indicate for Virginia, they would have 20 stations per kilometer. A 10 kilometer by 10 kilometer array is already in the range of 40,000 stations. 50 square kilometers, you're at 61 million. So you can certainly say that N is getting pretty large. So in summary, if you have dense recording of natural sources like aftershocks, you can do imaging, reflection imaging of structure by at least two different techniques, applying vertical seismic profiling techniques to the direct imaging, but that does require accurate source information. Or you can do seismic interferometry, which needs a good distribution of sources, but you don't really need to know with great accuracy where they are. And you can do this if there's enough sources in kind of a stochastic approach, treating it as though it's an ambient noise problem, or you can do it more as a deterministic interferometry approach, as is often used in the industry. All of this requires large 2D surface recording systems, which means large N systems, and to point out that maybe someday this can also be used to do not only 3D imaging, but 4D imaging of these active processes. Again, I want to end up by thanking all the people who are involved in this project, particularly our funding agency, the NSF Geophysics Division, all the personnel from Pascal that helped us with the instrumentation, for EarthScope for providing the instrumentation, a number of student volunteers, not only from Cornell and Virginia Tech, but from James Madison and Washington and Lee University, and particularly the staff of the Comfort Inn in Monticello, who made it a very comfortable field operation. Most of the processing that is shown in my work by Diego and DK was using the Vista software by Jedco, standard industry processing software. So I'll stop there and turn control back over to Andy and see if we can deal with some questions.
Great, thank you guys. That was awesome. So we have a few questions that have already come in. So I'll start by going through those. But if anybody else out there has some, this will be, as we start to do the ones that we have, that'll give you an opportunity to type them in. So the first question was from Philip Caldwell, and Philip was curious, out of the 148 Texans that you guys deployed, how are they time correlated?
They do not have a built-in GPS system, but they have a very, very accurate clock that drifts only a few tens of milliseconds per week. And therefore, these are basically pulsed at the beginning and the end of the week, and a linear drift correction applied. So we probably have of the order of 10 milliseconds of timing accuracy on those sensors over a 6-day deployment.
All right, thanks, John. Next question.
And I should note that the modern equipment that Larry showed have GPS built on board, so that's how it will be done with the modern equipment.
Okay, thanks. So next question is from Paul Freeberg, and Paul writes, in the back projection, how are you dealing with polarity flips? The stack will not work well for double couple events unless you are all on one side of the radiated energy. Question.
Absolutely correct. For the larger events, we're doing a cross-correlation and computing the polarity, which is where we're getting our focal mechanisms from as well, and simply flipping, multiplying the traces by -1 that are moving in the opposite direction. For the smaller events, we can't get the polarity very accurately, and what we're doing is we're just blindly stacking. And it turns out that the chances of your positives and your negatives perfectly canceling are near zero. In other words, let's say you have 65%, 2/3 of the stations are positive and 1/3 of the stations are negative. Although you will get some cancellation of energy, you will still get some constructive interference and be able to see where the earthquake was. And this is how we're seeing the very, very small events, that we're basically ignoring the polarity and hoping that they're not completely canceling one another.
All right, great. So I apologize to the next person. I'm probably not going to get your name perfect. I have a question from Blazvicik, and he asks, would using HypoDD produce better results for the earthquake locations early on?
I think the answer is always yes to that question. How much value you would find in that, I think you're then arguing. I think our relative locations were on the order of 50 meters, so I think you're improving that probably to 10 or 20 meters by using HypoDD if you wanted to. Or I should say by using the double difference techniques. We are doing a tomography, we're just not using the double difference.
Right, okay. So I have a couple questions from James Gridley, and the first one is for Larry. And James asks, how does your correlation method differ from standard surface-related multiple attenuation / prediction. It looks similar.
It's basically the same thing. It's just correlation is correlation. The only the concerns that might be different have to do with the balancing of noise. That is some sort of amplitude balancing techniques. We try a range of techniques to deal with the real noise so it doesn't overwhelm the stack after correlation, everything from sine bit up to various amplitude balancing schemes.
I'd like to comment on that one as well. When I've done some ambient noise method, I've used my standard industry software, and I've just used VibraSize cross-correlation methods to do the cross-correlation. So standard VibraSize, treated one of my traces as my vibrator.
Yeah, we did the same thing.
Okay, great. And so James had a second question, and that one is directed towards John. And he said he may have missed this, but he was curious. When you do your semblance stacking, do you account for the radiation pattern, or are you assuming an isotropic source?
I'm only accounting for the radiation pattern in the sense that we are doing the polarity flip, and we're only able to do that for the larger earthquakes, as I mentioned earlier. The back projection method does not include the amplitudes in any way. But yes, one could include this. If you did a full reverse time migration, one would also have to include the amplitude as a function of takeoff angle in there. And some people in industry have done joint inversions with a full amplitude included inversion that also inverts for the focal mechanism at the same time.
All right, thanks, John. So a question from Jiahong Lee. And Jiahong asks, could you comment on the usefulness of one component versus 3 component sensors in this kind of work?
Let's start, John.
Short answer is we'd love to have 3 component sensors within the active source community, but we don't. Industry is just starting to get there in a routine basis. So for the technologies we're using, we've not been blessed with that. But I think the simple answer is, of course, we'd love to have 3-component particle motion such that we can do these migrations with the full wave field rather than just with the vertical component of what we have. That would certainly help with the S-wave. We have done some S-wave back projections as well. They've been a little bit more awkward, and again, getting the amplitudes right when you're doing a vertical component of an S-wave gets a little awkward.
Another point of that is when you're doing interferometry and you're cross-correlating, if you have the surface waves and P waves in the same record, you start getting cross-correlation between P wave energy and S wave energy, and it adds greatly to the complexity of the result. Having 3-component data that would allow you to separate out the P wave motion from the S wave motion would allow you to do a much better job of getting clearer cross-correlating results that are related either to the P wave or the S wave without cross-contamination.
Yeah. So I think the short answer is we'd love to have 3 components.
Thanks, guys. Question from Christos Evangelidis, and Christos is asking, what about using envelopes in your back projection?
This is a commonly used method, but the main reason to use the envelopes is basically to lower your effective frequency content such that things will stack in. In our case, we had a good enough velocity model because we had the stations to build that velocity model, and I admit ours was pretty boring. But if you can build a good enough velocity model, you don't actually need to use the envelopes. You can actually either back propagate, back project, or reverse time migrate the full waveforms. So the envelopes will give you a lower spatial resolution by definition, I think is the short answer to that. And if you have a good enough velocity model that your phase is coherent, why not use the full phase?
Okay, I have a comment and a question from Kent Anderson, and Kent writes, although a full 2D array would have been ideal, the realities of deploying were limited given the sort of road access in Virginia. New technology, smaller footprint, longer deployment may minimize some of those permitting and logistical challenges, but not eliminate them. What are your thoughts on how enhanced instrumentation capabilities could help you better image the next Virginia event aftershock sequence?
Your backyard, John. You start with that one.
I think one of the responses is that when somebody's just experienced a magnitude 5.8 earthquake, they're very, very happy to have you on their property learning about what just happened. We got to the point where my Chinese student was getting hugs from some of the locals when he came and said, we're from the local university. So from an earthquake perspective, at least in the context of an aftershock sequence, I think you have a very, very easy job of permitting. In this particular area, we were a mix of longtime family farms and hobby farms commuting from Richmond, and a very, very, very friendly response when we talked to people. I do think if you're going to be using this in a place where they haven't experienced a large quake, or using something else as your sources, or using a lot of small background seismicity, such as some of the places in Southern California that have routine small seismicity, permitting getting across country in the farmers' fields for a month is going to be a little bit more of a difficulty. Absolutely. But yes, the small footprint, the fact that the footprint is really a trench that's a few inches deep and a foot long, the impact is pretty darn minimal of these systems.
I would also add that sometimes you run into obstacles that can't be avoided, like rivers and highways, but the oil industry has a great deal of experience of trying to compensate for irregularity to the surface spreads. So this is not an uncommon problem, and there's a great deal of experience of how to process data to compensate for a lack of ideal surface coverage.
Yeah, that's right. Gaps are normal in industry 3D as well. That's caused by an unfriendly landowner or a river or whatever, and there are methods to basically undershoot that spot. You lose a little bit of resolution, but you're still capable of imaging nearby. But yes, permitting is always going to be an issue. Less of an issue the smaller the footprint of the station.
Okay, great. So I think we're wrapping up on the questions front. We only have a couple left. So there's a question from Marino Prodi that I think I'll let you guys take a crack at, and I can also probably weigh in on it a little bit just based on my knowledge of this. But Marino asks, is the IRIS community asking the industry to develop cheap and modern instruments for thousands of stations of arrays of thousands of stations?
John,
Yes.
you can take this one too.
Yes. Those instruments that Larry showed you are costing, the 3-component instruments, I believe they're costing about $1,800 per station, which is about half the price of what we purchased the Texans for. And they're lasting a month and have built-in GPS and basically an infinite memory on them. So the answer is yes, and they're routinely deploying thousands of these instruments on their projects. The number of stations per day that they talk about when I talk with companies that do this, they typically deploy 100 stations per 2-person team per day. That's a routine number. So they have the technology right now, at least with geophones within the instrument. What they don't have is long period instruments.
That's right, and I'm not sure if Marino has heard this buzzword before, but there was a sort of a joint experiment called the Sweetwater Array that was deployed in West Texas last year, and that was a mixed mode array that included both broadbands but also nodal instruments, which are 10 hertz single component geophone types, but there are also 3-component versions of those that have a lower frequency cutoff, I think around 5 hertz. So I think the technology is certainly moving in that direction, Marino, and I think it's just a question of finding the right kind of joint interests that will push that ahead.
And I will say in my own work, and I've seen other people working with, for example, the Long Beach data set, that we've actually been able to use those 10 hertz or 5 hertz instruments down to several seconds quite successfully. But yes, it would be nice if we had something that could get down to 10 seconds and still be just as quick and easy to use in the field.
All right. Well, if there's no other questions, I think we'll. Maybe I'll just give everybody 1 second to type in 1 or 2 last ones if you have any.
I wonder if I could add one last comment that's brought up by this, and just to point out that the oil industry is routinely doing these surveys all over the world using these dense arrays. They're recording continuously, but the industry is only using a small set of that data set that corresponds to their shots here. So there's tremendous amount of data already being collected about natural sources that's sitting in disk packs with various contrasts around the world that's waiting to be accessed. And there are efforts to try to promote sharing of that excess surplus data with the academic community to do these kind of analyses.
All right, well, I haven't seen any more questions come in, so John and Larry, thank you guys so much for taking the time out of your schedules to share this work. I think it's a kind of an awesome, all-encompassing highlight of what you can do with dense arrays like this. So thank you guys again.
Well, thank you everybody for participating.
And folks, this will be recorded and posted on YouTube probably by the end of this afternoon. So if you have a colleague that you know is interested, you can have them look for it there, and we'll schedule another one of these webinar in roughly another month. So we'll see you next time. Thanks again, everyone.